Alrighty, good morning everybody. Welcome back to non-Euclidean geometry. Plan for today is I'm going to start off by doing something a little bit different. I'm going to talk about the upcoming courses in the math department for the spring and give you my thoughts on each one. And then we'll continue our discussion of neutral geometry by finishing off exterior angles theorem and looking at some examples and putting that into play. I've got my usual office hours today after class and from 2 to 3, and tomorrow at 10 and at 1. And your only homework for the moment is still take-home exam due Monday. So, one day a student went up to his math teacher and said, Miss Smith, I agreed to solve equations. I agreed to prove theorems. I'll even agree to do statistics. But graphing, that's where I draw the line. Okay, so here's all the courses that are being offered in the math department for the spring. I figured it'd be good to kind of give, just so you have a sense of what might be a good fit for you. I'm going to give you my thoughts on kind of what comes as a good follow-up to non-Euclidean geometry. What courses are kind of good based on what your interests might be. So first of all, mathematical logic. That's a class that only runs once every 2 years, and you are all eligible to take. If I put a check in the prereqs column, that means if you're in this class, you can take that class. So the idea behind mathematical logic is looking at the nature of what does it mean to prove something? How do you know if a statement can be proven or not? What does it mean to look at statements that can neither be proven nor disproven? And if you like statements like, if you like theorems like Gödel's incompleteness theorem, Megan points to Jack, you would like that class. I think that's actually a really nice kind of class that's, I would put it like a similar sort of difficulty level as this class, also in terms of level of abstraction. It's very much I'm going to put P for pure, because it's very much like a pure math class. It's not really looking at applications to the real world of any sort. But it's kind of exploring the underlying depths of logic and some set theory and the nature of provability. So it's a good like sophomore, junior level class, looking at stuff that you don't necessarily see in a good math liberal arts curriculum, but something that I think fits nicely with this class. Feel free to stop me at any point if you have any questions. So next up are linear algebra and Calc 3. These are both every semester. These are both ones all of you are eligible to take, since I think everyone here is taking Calc 2. If you're going to do a math major and you haven't taken linear algebra and or Calc 3 yet, you should take them soon. They are offered every semester, unlike mathematical logics. But basically, linear algebra and Calc 3 are the two courses that are kind of blocking off the rest of the math major. Once you've taken those two, you can take most courses that the department offers. And oh my gosh, linear algebra is like the most important math class you can like ever take in terms of being able to actually do math, because linear algebra is the shiznit. Calc 3 is pretty cool too. I'm an algebraist, so I prefer linear algebra. But also the other professors are bullies and haven't let me teach it yet here. So there's going to be 2 sections of it open for each of these. These are offered every semester. These are both courses that if you want to do a math major or applied math major, and these are kind of these are very necessary courses for both of those majors. You should take as soon as you can. Game theory. Game theory is an interesting course in that it's actually a course that you could either take for math credit or for econ credit. And it's very much an applied math course. But the idea behind game theory is looking at different models of cooperation versus competition. So class will look at subjects like, suppose we have two business firms that are each trying to sell the same product, and based on what the other company does, or what the first company does, the second company will alter its strategy and attempt to say, oh, you're going to do that, well, I'm going to do this to maximize my profit. Knowing then that the first company could come right back around and say, ah ha ha, but what about if I do this instead? And then they could either keep changing forever or reach some sort of equilibrium state where each company is happy. Or maybe the two companies decide, oh, we better cooperate with each other, maybe institute some sort of pricing controls, try to maximize our joint profits instead of our individual profits so that each of us make more money. We'll look at, I'm teaching this one if you haven't figured it out. We'll look at like voting strategies, like different systems of voting that can be put in place, which ones are more or less effective. Look at different ideas like when is it a good idea to file a lawsuit versus to take it to court versus to just settle outside of court. Different situations where you have multiple parties that are trying to that are either competing or cooperating in some way, and how do we do that most efficiently? It's a fun one. How often does this run? Good question. I had to fight for it to be offered this spring. Dr. Shalor has been teaching it as a summer course the past few years, and I think he might plan to do it next summer, but I'm not sure. As a regularly offered course, it's been 3 years since it was last offered during the academic semester, and I'm not sure. Look, we're adding discrete math as a regularly offered course. We're going to make number theory and non-Euclidean potentially offered more often. I don't know if game theory is going to be kind of cut from the curriculum, so you should take it while you can. Or take it during the summer, which is more likely to happen. Prereqs. I think the prereq says you have to have 310 or 320. But honestly, I don't really care. If you want to take game theory and you don't have either of these courses, just ask, and if there's room, I'll let you in. Okay, so next up, math modeling. This is very much an applied math course. It is offered every spring. It has been traditionally required for the applied math major to take it, although we just instituted a change going forward that now instead of requiring math modeling and probability, now you can take 2 out of 3 of probability, math modeling, and differential equations for the applied math major. But math modeling will involve sort of looking at mainly how do we use programs to do lots of optimization. So like kind of following up with ideas from calculus of how do you maximize your function? How do you minimize your function? Looking at a lot of like real world examples of things you might want to maximize, minimize. Math modeling, you'll learn a lot of some amount of coding for how can you use computers and write programs to help you do this sort of optimization rather than trying to do everything by hand like you would in the Calc 1 class. It's a good one. It's a really good one if you're thinking of going into any sort of industry job, working for a company that uses math. Math modeling is a good one to take. And math modeling, yeah, is as a 310 prereq, so linear algebra. Next up is real analysis. I've mentioned this course several times this semester, in that while in non-Euclidean we spend a lot of time looking at different forms of geometry that you may not be used to thinking about, including like R2, but also looking at weird models like the unit disk, spherical geometry. How can we do geometry when there's only 4 points in all of existence, that sort of weird stuff. Real analysis is all about Rn. So the number line R1, R2, R3, which is 3-dimensional real space, and it is one of the 2 big, quote, big scary, unquote, courses of the math major. It's required for every pure math major, and every applied math major has to take either real analysis or abstract algebra at some point. But that course will involve a lot of proofwriting, some amount of group work, maybe some presentations if depending on the size of the classes. It's a fun class. I'm teaching that one too. It's offered every spring. All of you, even you, should probably take real analysis at some point before you graduate. I tried not to point to anyone in particular when I said that. You should also take abstract algebra because that's actually my baby, but real analysis is a good one too. And that has a free 20 pre-req. Any questions or comments so far? Should I keep going? I'll keep going. Next up, the 2 topics courses. Statistical learning. That's Dr. Trelord's baby. That might become a regularly offered course. Right now it's just a topics course that has happened to run every 2 years for the last several years. I wouldn't be surprised if it ran again 2 years from now. But the idea behind statistical learning is how can we sort of use computers, sort of a course that involves a good amount of programming. How can we use programming to sort of train computers to think for themselves? So it involves some amount of statistics, some amount of looking at AIs and how do they work. Sort of different from, a little bit different topics than Dr. Seifert's current AI course, but some amount of training, thinking about how do we train computers to think. And yeah, that's a really good one if you have an interest in, it's a good one to take if you have an interest in programming, learning more about computers, learning about some more advanced statistics. And that one has a prereq, has 2 prereqs. You need linear algebra and 370 for that one, which is probability. Probability is on every fall. Next up, numerical differential equations. This is a one-time only course that basically is a combination of differential equations and numerical analysis. Dr. Bolasov is making all of her students in her cult take it. I think any of those are in here. No, this will drop the class. So the idea behind numerical differential equations is how can we solve differential equations, meaning equations involving derivatives, when we can't actually solve them exactly because they're too hard. Instead, how do we approximate solutions? The solutions to this differential equation are going to look something like this. And they'll probably involve a little bit of programming, if I have to guess. Will involve lots of looking at equations. It's a good one, I think. Who do I recommend this for? It's a good one if you're interested in going on to grad school in math. Knowing about some, especially in applied math. Knowing about how differential equations work is always a good thing. There's a lot of differential equations in higher math. Numerical analysis, especially if you're an applied math student thinking of going on to grad school, I would definitely recommend this one. And finally, to end the trail of pap, we have topology, which is once every 2 years course. As a 310, yeah, 310. By the way, for the numerical differential equations, you either need differential equations or numerical analysis. Either one. Not necessarily both. Topology is 310 prereq. Topology is sort of like this class, in the sense that it looks at sort of abstract mathematical spaces and looks to see what can we prove about them. Specifically in topology, you're looking a lot at what does it mean to have an open set and a closed set. And how can we generalize that to beyond just being an open set is like an open interval in R1 or inside of a disk in R2. What happens when we generalize that? What happens if we want to do calculus in spherical geometry on the surface of a sphere? Or on something that isn't necessarily Rn, but behaves similarly to Rn. Topology is a fun one. It's definitely an elective course. It's one I would highly recommend if you're thinking at all about going to pure math grad school. It'll be a fun one. It'll involve probably a fair amount of proof writing. And yeah, that's my thoughts on that. So yeah, what questions do you have about any of these classes? Or do you not have any questions and I shouldn't have bothered doing this because you're all lemmings who just do as you're told? Yes, Steve.
Would it be a bad idea to take real analysis and topology at the same time?
Ooh, double whammy. How much do you enjoy writing proofs?
Not bad, I guess. I don't know.
Not that bad. That sounds like,
This class they're fine, but just don't expect
not
to
nice.
yeah, don't expect to do too much else. Yeah. I will say this, I've taken multiple proof courses, and like I think I junior and undergrad at the same time. It's a lot of work. You will spend a lot of time flitting back and forth between office hours, I'm guessing, if you do that. They're both really, I mean, they're both subjects that are really near and dear to my heart, but you're going to have to get used to thinking a lot about doing math abstractly if you do both of those at the same time. And those are both courses I would classify as being a lot of work. Like the proofs overall, I would say, are maybe a little bit harder for each of those classes than the ones we're doing in this class, so to speak. But by that point, you'll also be more used to proof writing and be a little bit stronger about it. Right, Becca? It's not, so overall, I guess what I'm saying, it's not for the faint of heart. But it is feasible if you're willing to put a lot of time into it.
probably not.
I may have scared you away.
It's like cringy.
I'm trying to be honest with you. Like, what I want to say to you is like, oh my god, you should take both those courses. They're so great, awesome, and fun. But just know that you will work a lot if you do both of those. And on similar types of stuff involving proof writing. Yes.
Related question, how about topology and game theory? What is like workload-wise, what does game theory look like?
Ooh, okay. So topology and game theory are two. So topology and real analysis are going to be very similar types of classes in terms of workload, I would expect. Topology and game theory is a different story. Game theory is mostly kind of computation-based. Like I'm planning for that class to have like weekly quizzes, sort of like what we're doing in here, and less like big homework sets, and less in the way of like big homework sets. Whereas topology, I would expect to be less like in-class quiz, exam stuff, and more lots of proof writing. So if you like the proof writing aspects of this class and the in-class quizzes aspects of this class, then yes, I think those two are kind of make a little bit better of a fit together than topology and real analysis. Mainly because they're not looking at the same types of math. You'll be thinking in different ways and in different aspects for those two classes. Yes, sir.
Who's teaching topology?
Actually, let's go down the list. Dr. Gabler, Dr. Hutchinson, Dr. Gabler, me, Dr. Webster, me, Dr. Chalor, Dr. Volosov, and to answer your question, Jared, Dr. Murphy. Yes, Anna.
How heavy on the econ side versus math side is game theory going to be? Like,
Let me tell you this. I have never taken an econ course in my life. If that answers your question. They should not have let me teach this course. I'm in no way qualified. No. I'll say this: like we're mostly going to be focusing on mathematical models, and we'll draw in some like examples from economics, like mainly like, oh, these two businesses are competing and they're setting a price point and blah blah blah. But I will not assume any prior knowledge of econ because I don't have much prior knowledge of econ myself. But yeah, I will say it is. I'm planning to teach it as a math class, but it does give you econ credit, and we will be doing some econ-focused examples. Not exclusively, but a fair amount throughout the semester.
Are you going to teach real analysis the spring afterwards too?
But no, I'm gonna guess no. I'm gonna guess because I'm guessing in a year from now, Dr. Gabler's going to try and swipe it back from me. I had to fight him for it I had to fight him for it this time.
He does like his analysis.
I mean, well, yeah, well, that's the thing. Dr. Gabler is the analysis person within the department. That's like that's his specialty. Whereas my specialty is not really real analysis, and it's definitely not game theory. It's abstract algebra. So, I don't know who's going to be teaching it. It'll most likely be Dr. Gabler, but it also could easily be me, Dr. Murphy, or Dr. Hutchinson. It's probably one of those four, I guess. Oh, I almost forgot I need to talk about these two. Yes, any questions for him?
So for game theory, how do you sign up for it as an econ versus math credit? Does it depend on what you search in WebAdvisor?
Yes, good question. So basically, this actually has two different course numbers, Econ 375 and Math 375. If you want to sign up for math credit, sign up for Math 375. If you want to sign up for Econ credit, sign up for Econ 375. It makes zero difference to me what you sign up for. I think right now, like, the registrar has it so there's only 5 open slots for the Econ version and 20 for the math. If one of those fills up but not the other one, and you want to get into the one that's filled up, just let me know. I will let you into the other one, because I could not care less which one you sign up for. I'm not, yes. Also to clarify, like, the students taking it for Econ versus math credit are not going to get different types of assignments or quizzes or anything like that. It's exactly the same course. The numbering was only what do you want to count it for credit points. Yes. I don't know, what do you want for it, Elaine?
I think we're going to take it for math.
For math? Then I expect you shouldn't have any trouble with it. If you do, let me know, and I'll take some butt to make it work.
I've never had trouble getting into a class, and now I can register this year. So.
Well, aren't you special?
I'm guessing you can't like switch which it counts for down the road then?
As far as I'm concerned, you can. That's between you and the registrar.
Yeah, okay.
I will say this. This will be my second time teaching game theory. First time I taught it, I think like a month into the course, I had a student want to switch from Econ credit to math credit. That was an email to the registrar. They said, sure, no problem, and I don't see that being a problem. If you try and do it like the last week of class or something, then the registrar might take issue. But I will not personally take issue, and we'll fight to say, yeah, let her do it. It does not matter to me. Don?
Of the 400 electives, what would you recommend?
If in general or for you specifically?
Of all of the, just in general.
The 400s, take real analysis. I want you all back. I will say this. As a follow-up to non-Euclidean geometry, I think these two, real analysis and topology, work very well as sort of a follow-up to this class.
Oh, I mean the electives, the 400 electives.
I think topology works very well as a follow-up to this class. I say, because all these bottom three in these two, well, actually no. Math, logic, game theory, and these bottom three are all like elective courses, I would say. They're not required for anyone. And out of these three, I think topology works best as a follow-up to this class and looking at similar types of things, but like one level of abstraction deeper / harder. If you have any sort of applied interest, like interest in programming and such, this is probably your best bet. If you have an interest in applied math grad school and hanging out with Dr. Volasov's cult, this is a good one for you. But topology is definitely my favorite of these three. If you're like interested more in pure theoretical math, I think it's the best. It's certainly the only one of those of these three. But these two would probably be better fits if you're thinking of something applied in some way. That's more of like an individual sort of question, I would say. Let me talk briefly about these before I forget. Pure X. That, you need 101, you need that, you need 101 for that. I think every math major should take at least one programming course. Yes, even the pure students. What's that mean?
I said, I'm in one, calm down.
It's too late for me.
Oh, I wasn't looking specifically. I was looking in this general direction, but like, sorry.
No, too late.
Yeah, maybe even you. Because this is, in all honesty, programming is such a useful skill in the modern world. Everybody needs to learn how to write and understand some amount of code. If you're thinking pure math, then maybe you just like one course to wet your feet because you'll probably have to do it at some point in your life. But especially if you're thinking of applied math in any sort of way, I think you should take at least have a couple programming courses. And that could take the form of math modeling or something like numerical analysis, which is a required course to be applied major that's offered every fall. And those are really good courses to take. Those kind of give you some experience with programming, but we've got this computer science minor. It's officially been approved as of earlier this month. We want to populate it, and we think it's important for students to take this. In fact, it's going to be a requirement for applied math students coming in, not for current ones, but ones coming in, that you have to take at least one computer science course for the applied math major. Honestly, I would have liked it if that was the case for the pure math major too. So this is offered Intro to CS is offered every semester. Will be offered every semester. I think the plan is to have 2 sections every fall, 1 every spring. Data structures is basically the follow-up to the intro course, basically picking up where it leaves off, looking at more advanced programming techniques and types of code and yada yada. And models of computation, you learn how to compute things with various models. I don't know how often this third one's going to. I think every semester, every spring, every 2 years, question mark? I'm not sure about how often that third one's going to be offered. Dr. Seifert's a cool guy. You should take it first. Any other questions? Well, there's been a lot more questions in my discrete market. Hold on. Before we move on to some geometry. Yes, Jeff?
Is models of computation just like a more computer science focused version of math modeling, or are they more different than that?
I'll be honest, I'm not sure.
Okay.
That's a good question for Dr. Seifert or Dr. Tolwer, I think. Looked at these courses. I think models of computation, I'm guessing, looks at the theory of like, oh, you can carry out this algorithm in polynomial time versus an exponential time type questions of like in terms of looking at like different models of efficiency for how you can write different types of code and how long you would expect it would take it to run. Whereas math modeling, I think honestly this course might be a little bit more of an abstract pure math beat course than mathematical modeling, believe it or not. And that, but we'll also certainly look at how do you also write different types of code, different models of code in ways that can solve real world problems as well. I'm not exactly sure what the difference is going to be between the two, but that's what I've gathered so far. Yes, Luke?
I'm just curious, do you know if they're possibly going to have the 101 as a summer class?
That's a good question for Dr. Seifert. If he's interested in teaching it as a summer class, then yes. If not, then no. So I have no idea what his intentions are in that regard. I will say this, I know he taught a summer course this past summer. Not for us, but for the college he was coming from. So I know he is not entirely unwilling to teach summer classes as a general rule. I'm guessing, if I had to guess, I would guess he might if there's enough interest in it. So if you let him know you would be interested in doing that as a summer course, if you can get enough students involved, he might be willing to do that. But that, I don't want to put words in his mouth. That's something to talk to him about. Side note, I want to teach this at some point. If Dr. Seifert goes on sabbatical, Dr. Bolsov and I will duke it out to see who gets to teach intro to programming for him. I graded an intro programming class in undergrad. It was fun. I had a lot of friends in there, and I just got to trash all over their code. Are there questions or comments before we get back to geometry? If you have any more questions about any of these classes, like whether they're a good fit for you, like specifically, I'd be happy to talk to you outside of class. Feel free to come by my office hours. And we can talk, and I can give you my opinion, maybe like an opinion more specifically for you if a certain course or combination is good or not. All right, let's do some math. So if you recall, last time we were in the middle of proving the exterior angles theorem, which was the theorem that says, given any triangle in a Hilbert plane, any exterior angle to that triangle is always going to be bigger than both of its remote interior angles. So for this picture that I've drawn over here, we know ACD, for instance, this angle is going to be supplementary to angle C inside of the triangle. So this is an exterior angle. And so what the exterior angles theorem says is that this angle that we have here should be bigger than this one and this one. Not necessarily that one, but the remote interior angles. And our proof was based around looking at how do we compare the size of this angle to the size of angle A. And we said we were going to show that this angle is bigger than angle A, and that showing that it's bigger than angle B is pretty similar. So here's the scoop. Our way of showing this was to say, well, we know one of these must occur. That either angle ACD is bigger than angle A, that it is smaller than angle A, or what was the third possibility? Yeah, that they could be congruent. You're all actually proving on your take-home exam that one of these three things has to occur. We showed last time that this leads to a contradiction, that if they're congruent, then that means we can, if they're congruent, then basically the line AC acts as a transversal to the line CD and AB in a way that forms congruent alternate interior angles, which means that AB would have to be congruent to the line CD, or not congruent, parallel to the line CD, but which clearly can't happen because both lines have B. And so this bottom case led to a contradiction. And so to finish our proof, we're also going to show that this one also leads to a contradiction. The case where angle ACD is smaller than angle A. So let's look at this case. These two. Angle ACD is smaller than angle A. So what does that mean to say that angle ACD is smaller than angle A? What does it mean to say that one angle is smaller than another angle? David?
That there's an angle inside A to which ACD is congruent.
Yeah, that's exactly it. That means that if this angle is bigger than that angle, then we should be able to find some angle, we should be able to kind of cut angle A off at a ray in between. So let's say some point E about here, so that angle CAE is congruent to angle ACD. And that's what it means for angle A to be larger than angle ACD, is that we can cut this angle off at a new ray so that EAC and ACD are congruent as angles. So if we write that down, we can say then there exists a ray AE between AB and AC such that angle ACD is congruent to angle EAC. So we'd like to show that this somehow leads to a contradiction, just like with the congruent case. Turns out that the contradiction we can arrive at for this one is pretty similar to the contradiction we arrived at in the congruent case. Because we said, oh, if this angle is congruent to angle A, then alternate interior angles theorem told us that two non-parallel things have to be parallel, which is our contradiction that we ended class with last time. Turns out we could do a similar sort of contradiction here, in that we're going to consider the line CD, and this time the line AE, and show that those two lines have to be parallel. So then since congruent alternate interior angles are formed, with the line AC acting as transversal, to the line AE and the line CD. In other words, if we think about the line CD here as intersecting line AE and line CD, since this interior angle is congruent to this alternate interior angle formed by the transversal here, AC. Since AC causes AE and CD to have congruent alternate interior angles, what does that tell us about AE and CD? AE and CD are causing some congruent alternate interior angles to be formed. Right?
Parallel.
Yeah, AE and CD would have to be parallel. By which theorem, Elaine?
The alternate interior.
Oh, how appropriate, the alternate interior angles theorem. So by alternate interior angles theorem, AE and CD must be parallel. Can that happen? If we look at our picture? Here?
I don't think so. Wait.
So here the question is, can the line AE here formed and the line between C and D are actually parallel to each other?
Yeah, well, the answer is no.
Okay, why is it no? And your answer cannot be, because Dr. Gerstle, we're trying to arrive at a contradiction.
I don't know how to say it yet, but it's probably going to involve between this, and the problem's going to be point B. Like our contradiction might be with point B.
Point B?
Because it's past the ray AE, so I don't know how to say it.
I don't think point B is necessarily going to be the trouble point, because I don't think AE has to pass through the point B. In fact, I think we can even show that this line can't possibly go through the point B, because then we have two unique lines through both A and B, which would contradict instance axiom 1. Right?
Okay, so because ray AE is between rays AB and AC, there has to be a point on ray AE that is between points B and C.
Like here?
Yeah.
How do you know?
Between this.
Is there a between this axiom that tells us that?
No, but I think based on the definition of between, it's a ray. Or, yeah. That's the best I got.
Okay, Katie?
Well, they're just not parallel. If you extend the ray, it intersects.
It does? How do you know that if we extend the ray, it doesn't do something like this? This is actually a serious question, even if I'm drawing a silly picture. Turns out that there's a theorem that was in one of your packets that we never actually proved called the Crossbar Theorem. that actually guarantees that if if ray AE is between AB and AC, then AE and BC have to intersect.
See, that's what I said.
Yeah, but you were just like, it's because of betweenness.
Yeah, but that theorem's from betweenness, isn't it?
I mean, you're not wrong. It is a theorem that can be proven from the betweenness axiom, but it's not necessarily a result that's obvious just from the betweenness axioms, I would say.
So I'm not wrong, I'm just not right.
Yeah, let's go with that.
Can you also prove it not RAA by having, having with, the perpendicular theorem where we have point A and we make a perpendicular to BCD, AE.
The problem is that AE doesn't necessarily have to be perpendicular to BC. All we know is that we're assuming that there's some point E such that EAC, let's say, is congruent to ACD. But it could look something more like this instead. I think the initial picture I drew looked like it was going to be perpendicular, but I don't think that's guaranteed by perpendicularity.
No.
Perpendicularity is not guaranteed.
Oh, no, I was trying to say that couldn't we avoid the whole RAA argument to begin with and just take the triangle ABC with the point D, the extension. You have point A, and with the perpendicular theorem,
Use the theorem we talked about last time to find the line passing through A that's perpendicular to BC.
yes, and then make a line perpendicular at,
On another color.
and then, call it point F, I guess. And then make a line parallel to AF at A.
What do you mean by parallel to AF at A?
Sorry, perpendicular. to
Oh, like
AF
this?
At A.
Okay.
And then wouldn't AC be a transversal? Making ACD and, I guess, GAC,
What's your G?
a point on the line,
Something like up here?
yeah, on the other side. GAC would be, because of the alternate interior angles, GAC would be equal to ACB, but GAC is greater than BAC.
Okay, GAC is congruent to ACD, which you can use. Technically, we would need the converse to the alternate interior angles theorem.
Okay.
Alternate interior angles theorem says if these angles are congruent, then the lines are parallel. We would need an extra result which says if the lines are parallel, then these two angles have to be congruent.
Okay.
But if you were to prove something like that, which is not generally true, but would be true in say R2 and like a Euclidean plane, not necessarily an arbitrary Hilbert plane, then you could do something like that.
Okay.
We would need some extra machinery to make your idea work, but I think that could lead to something. Where was I? So, however, by the crossbar theorem, lines AE must intersect the line BC, which is the same line as CD at some point, causing a contradiction. And here, this is based off the fact that the ray AE has to be between AB and AC. Thus, angle ACD is not less than angle A. And then we can say that we've eliminated the second case, and since one of these three cases has to hold, and it can't possibly be the case of ACD is less than angle A or it's congruent to angle A, the only remaining possibility is that angle ACD is strictly greater than angle A. Thus, is angle ACD is strictly greater than angle A. And there's our proof. Technically, we would then need to go and also show that angle ACD is also greater than angle B, but you can do that pretty similarly to our argument for angle A. It just ends up being a similar sort of eliminate the case where it's less than angle B and congruent to angle B using the alternate interior angles theorem. Any questions or comments about this result? Yes, John.
What is the crossbar theorem?
The crossbar theorem basically says that if you have two rays like this, we'll say call this point A, call this point B, call this point C. If you take any ray in between AB and AC, like say a ray like this, where this is some point, call it D, then this new ray, AD, that's formed has to intersect the line from B to C.
Okay.
It's called the crossbar theorem because it sort of looks like a crossbar. It sort of looks almost like a crossbow. If you're thinking in terms of weapons. I'm kind of thinking in terms of weapons because we spent most of my Calc 1 class this morning talking about firing cannons at castles. Good stuff. Does that make sense, John?
Oh, yes, it does.
Yeah. So in this case, since AE is between AB and AC, ray AE would have to intersect the line that goes between B and C, which happens to be the same line that goes between C and B,
Okay.
which is our contradiction. There are questions or comments? I feel like starting something new with 3 minutes left. When we come back on Friday, we're going to look at spherical geometry again and see, do these two theorems, alternate interior angles theorem and exterior angles theorem, hold? Yes, Helen, that's very key. Do these theorems still work in spherical geometry, or does something go wrong? And then we'll talk finally about the theorem that says that gives you a way to break up angles into degrees and or radians. So hope you all have a good rest of your day. I will see you all on Friday. Feel free to